Okay, so today we're going to talk about the synthesis stage of the design flow. This is a very common stage in multiple areas, whatever you're doing, whatever area you're designing, like if you're doing modules for image processing, for video encoders, or just simple VLSI circuits. You want to synthesize them, because you don't want to do the layout manually, you want to synthesize your circuit and have the layout generated for you. So this is a very common step for many students in our group and in everybody working in VLSI. Do you guys remember that we ever talked about synthesis? You have a general idea what it does? So let's remember that. You wrote your Verilog files in a behavioral level, meaning you didn't specify any gates, any connections. You just specify how your code is going to behave with for loops and if statements and all those things that are not compatible with hardware directly. So what you want to do is that you want to take that code and transform it into gates and schematics. So that's everything that the synthesis stage does. It takes those Verilog files, and at the end it will give you one single Verilog file. But what's special about this Verilog file is that it contains information about only gates and how gates are connected, nothing else. No if statements, no for loops, nothing behavioral, only structural. You could do that either Verilog or via HDL. Right now we're going to do Verilog, but if you want to do it via HDL, you could. This Verilog file that we get, we're going to take into another software called Encounter, which is part of Cadence. And with a single command, single script, we're going to get the whole layout of our design. And if we still have time, we're going to take this layout into Cadence and maybe extract the spice parasitics and simulate that. We're not going to simulate it, but just extract it and do that. Okay. So, just like we always do, TCSH, and then I already created a directory here called lab3. So what I want to do here, okay, I've placed my Verilog files in this folder called source. It's always a good idea to have a separate folder for your Verilog files. This is an old project that I did. It has a multiplier, divider, and square root unit, and this is what I wanna synthesize. Now, the software I will use is called Design Vision. Oh, I'm sorry, I should do cat setup 45 and then start Design Vision without an N. Okay. Now, Design Vision is a single component of a large software suite called Synopsys. So Synopsys is not equal to Design Vision. It's equal to Design Vision plus many other things. HSpice is actually part of Synopsys, as is Cosmoscope. Okay, now here there's an easy way and there's a hard way. First I'm going to start with the easy way. Actually, the easy way doesn't even require you to start this software, so let's restart. The easy way is to use a script file and run that script to do the whole synthesis process. That script I have here, it's called compile DC. I'm gonna send you the script because you're gonna need it to do the synthesis. But for now, let's go there and check this file out. Now, this file has two regions. This region here are your variables, and this region here, you don't need to do any modifications. You don't change anything. Here, you specify your files and everything else. So let's start. Here I should specify what are my Verilog files. or VHDL. So what I want to do here is I have my files in a folder called source, right? So I'll just do source/star. This means take everything that's in that folder. Be careful to have, actually no, that's a bad idea. I don't want him to take everything in that folder. Actually, in my case, I do want him to take everything in that folder because everything is synthesizable. But if you have a test bench, by the way, you don't synthesize your test bench. Test bench, remember, is a separate Verilog file to simulate your design. You don't take that for your synthesis. You just take the parts that make out your circuit. You don't take your test bench with you. Okay, so let me get back here. If this syntax doesn't work /star, I'd have to list them individually, all my Verilog files. Here, I have to specify the name of my top module. I don't really remember that, so I will go here and check again. It's called top. That's what I called it, which is very convenient. Here it's whatever you call your module. Okay. Here in my case, I happen to call it top. Usually you have a clock in your circuit. You don't always have a clock, but 95% of complex designs have clock. So you should specify the name of your clock port in your design. It could be clock, CLK, it could be my clock, it could be whatever you named it in your Verilog file. Here it's clock. Here it's the frequency of your design. Initially you don't know what frequency you're gonna operate in. You don't know what your design allows frequency. You don't want to give it a too fast frequency, too slow. So it's actually best to start with a slow frequency, right? And this is in megahertz, so let's specify 100. Okay, now Design Vision is going to tell me if I can increase it later. The input delay is in nanoseconds, meaning after how long are my inputs going to arrive to my module after the clock edge. So if this is the clock edge, how much delay after the clock edge are my inputs going to arrive to my module? It's safe to leave these values as 0.1 and the output delay also as 0.1. Now here I don't have to change anything except if you're using the HDL, you change here analyze F Verilog to the HDL. And that's the only thing you change in this area here. Okay, that's everything you need to do. If you look at this command here, this is what you need to run to compile this file, to run this script. It's dc shell t f compile dc.tcl. So this is what I need to run. dc actually just think it's like that. dc shell t f compile. Okay, and I wait. Now this process can take up to 3 hours if you have big circuits, and especially if you give a very high frequency. What happens is that design compiler here, oh, I have errors. Okay, let me check. Probably didn't find the files. Yeah, wasn't able to open the files. Okay. Source. So I just have to put them there individually. I'm sure there's a way to specify them all together, but can't seem to remember it now. Source. Okay, let's try again. Okay, it's working. Now, if you notice here, it will tell you what registers you have, how many bits they are, and what's their type, flip-flop or latch.
This is for the input and output values?
What do you mean?
I mean that when it specifies registers and flip-flops, maybe it is like the registers for the input values and output values, or within the circuit.
It's the registers that you have in your Verilog file.
Because mainly when I program using the behavioral level, I didn't like specify registers.
If you're doing behavioral, you have to have registers. You can't do behavioral without registers. Anyway, so you can see now it's compiling. Maybe I should have chosen a smaller design here because it would have taken less time, but basically you have to wait now. If you give a high frequency to your design, then it will take much longer because it will try to put buffers and try to reorganize your circuit to meet that frequency, the high speed frequency. So if you lower the frequency, it will finish faster. Okay. Okay, it's done. Now you'll have some errors, some warnings. Most of them are harmless, except if it fails to compile at all. Then you actually look at the errors and warning. Or if sometimes it tells you have pins that are shorted together, ports that are connected together, or floating nodes or something. These are worth looking at. Anyway, after it's done, you would have some files generated. The important ones are, let's see. Okay, power.rep is the power report. This is the timing report. This here is my is a netlist that I can get, is a Verilog netlist that I can get the layout from later, which I'm gonna show you now. And this is my cell report, and this is my Synopsys design constraints. This is another file that you need to generate the layout in Encounter, which I'm gonna go with you now. Okay, so you're gonna have 3 important reports and 2 files, top.vh and top.stc.
What is the structural Verilog file?
Okay, let's take a look. It's called .vh, but it's actually Verilog, not VHDL. So this is what it looks like. It's just a normal Verilog files, but if you notice, it's just structural. FAX1 is a full adder. INX1 is an inverter. N2 is a 2-input AND gate. And that's all it is, just connecting stuff together. You can see it's a very, very big file. Very user unfriendly.
The output is a file.
Yes.
schematic.
Yes, the output is a file. Okay. So let's see how we can generate a layout from that. Generating the layout is just as easy. You just need to run a script. You don't need to run the software. For this, you need to modify a script called encounter.configuration.conf. Okay? And you specify here your top level. What is my top level called? You guys remember? Top. So I just enter top. I don't change anything here. I don't change anything here. Okay. I don't change anything except for my top level name, module name. Okay? Now, if you guys might be new, because you might not be familiar with modules and stuff because you didn't see the Verilog lecture last two weeks ago, but imagine like you know what module means and try to keep up. Okay. So to generate my layout, I run this script, this command, encounter init, right? Encounter.tcl. Now encounter.tcl will take the information from encounter.conf, but you don't modify it yourself. You only modify encounter.conf. And these two files, encounter.conf and encounter.tcl, they will be generated in your directory whenever you call the CAD setup 45 command. So I don't need to send you these files, you always have them. I just need to send you the compile DC file. Actually, I'm going to modify the CAD setup 45 command to generate the compile script too in your directory. Okay. Also, this could take up to hours if the design is big. I don't think it's going to do that now. Now, Encounter is part of Cadence. Design Vision and Design Compiler are part of Synopsys. Now what's happening here is that Encounter is doing an operation called PlaceandRoute. First it finds the optimal way to place all my cells, AND gate, the full adder, and everything else, and then it finds the optimal way to connect them through multiple layers. And what you see here on the outside are the VDD and ground. One of them is VDD, one of them is ground. How many transistors? I don't know if there is actually a way to tell. You would just report netlist statistics. Maybe not. Report gate count. But you can see it's pretty beautiful. If you zoom in enough, you'll see the individual gates. For instance, this gate here, let's see what it is. Edit. Not sure how I can check. Key. Oh, this is an AND gate here. Anyway, the red is poly. Let me check. Actually, I'm not sure it's poly. I don't think it's poly. Hmm?
The window you open is
Oh, really? Yeah. Anyway. This is VDD. Now the reason that you see VDD and ground like that, two wide wires around the chip, is to protect it, to insulate it from outside coupling from outside with outside capacitance. You could turn off objects here in order to clarify your design. Anyway, here I can actually, let me check the report one last time. Do it as HTML and display it. The report actually here is pretty nice. It will tell you your area, it will tell you your gate count. It won't tell you your power. You can see an estimation of power in the synthesis report anyway. But okay, now say I want to take this design to Cadence, and in Cadence I want to see it in my layout editor, and in the layout editor I can export the netlist, SPICE netlist. If I want to, I could simulate it. So what I do is that I save my design as DEF. DEF is a file format that describes layouts. I could also use GDS, which is very popular. The problem with GDS is that you need the second file, a map file, which maps the different layers into the different numbers to different layers, which Cadence needs. But DEF, you only need single file, and you can easily open it in Cadence. So I'm going to save all these, save route, save netlist, save standard cell. I'm going to call top.def. Okay. Yes. Let me see my report that I generated. Summary report. It's empty for some reason. Okay, that is weird. Oh, I forgot to show you the reports that I got from my synthesis. Let's see the power report. Remember, this was generated earlier in my synthesis. VI power report. It will tell you your library, your operating voltage 1.1, your time units. Here you see the internal power and the net switching power. The internal power is the short circuit current when both PMOS and NMOS are on while the gate is switching. Remember, there's a very short period NMOS PMOS is on. Net switching power is the charging discharging of the gate capacitance of your transistors and other capacitance. And this is the total dynamic power, the sum of these two. And the leakage power is pretty, it's not actually that small in this case. It's about maybe 7%. my total power. So you have that, you have cell report. It will tell you all the cells that you have. It will also tell you the total area from the cells. And finally, I have my timing report. The timing report you could use to see if you can increase your frequency or not. Here, okay, first let me explain the slack. Anybody has any idea what the clock slack means? Okay, now remember we talked about setup time and hold time, and that the signal should arrive before the setup time before the clock edge. Now the slack is how early are my signals arriving before the clock edge. My slowest signal, how much time does it still have between it and the clock edge? This is important, so just, what is this? Okay. So this is my clock, right? Now I have a lot of signals in my design. Let's say my slowest signal will arrive here. Okay, here it's still computing, and here it arrives on my clock. This, how much time do I still have before the clock, is called my slack. If this is positive, my slack is positive, it means I still have room. Okay? I still have room before the clock edge, and I can actually increase my frequency. I can reduce my clock cycle. So this is good. If my slack is negative, it means my signal is actually arriving here. So if the slack is negative, if Synopsys tells you that your slack is negative, means your circuit will not work. It will fail to work ever with the frequencies that you gave, because your signal cannot make it in time for the clock to arrive. So this is good. This is very bad. So always check your timing.rep, this file, to see if your slack is negative or positive. I happen to have a positive slack, 5.84 nanoseconds. So I add that to my previous clock period, and then I compute my frequency. My previous clock period was, I had 100 megahertz, so it was 10 nanoseconds. 10 nanoseconds. So I can actually decrease it by 5.84 nanoseconds. So what would that make? 4 nanoseconds? So let's say, to be safe, let's say 5 nanoseconds. So I can actually have a clock frequency of 200 megahertz. And that's how you know how much frequency you can have in your circuit. Okay, now what you see here is the critical path. The critical path is the slowest path in in the whole circuit. And this is what dictates your slack. You only look at the worst case to see your slack. Anyway, okay.
Can we do further simulations with the out and the encounter program? Like, for example, can you compare it with smoking and schematic?
No, you can't do that there.
Just take it as an hour?
What you can do is that you can take it into Cadence. I'm going to do that real quickly here. And you can do LVS in Cadence.
I can take it from counter to Cadence.
Mm-hmm.
To use
yeah, that's what I'm doing now. I'm gonna do it real quickly because I want to go back to Design Vision and show you other features there in Design Vision. Okay, first thing I want to create a new library. Let me call it lab 3, and I want to attach it to NCSU. Okay, the way I get that layout from Encounter is I need to import that DEF file. So I do import DEF. The DEF file is dop.def, and this is the name of the library I want to place it in. I call it lab 3, and these are the libraries, the reference libraries, meaning which libraries is that layout using. I know that it's using NCSU, right, because it's based on the 45nm library. So I just need to write down the libraries that it's using. So it's NCSU TechLib free PDK 45, which has all the layers and information about the layout, and analog lib, which should always be there, and free PDK 45 cells, which contains all the cells like the full adder and the end, the OR. Okay, here the name of my target cell, I'm gonna call it top. Target view name, layout, and this is everything. I hope I didn't forget something. Let's see. Defin failed. I haven't done that in a while, so I must have forgotten something. Warning, error cannot set duplicate reference. Okay, let me try that again. Create a module hierarchy from hierarchical names. Let me take it into a new library and tell it to create the new library, and take the technology from NCSU devices. Oh, actually NCSU TechLib, and I remove that from here. Okay, let's try that again. Okay, it completed. Row for row. Select that one side. This is probably not very critical. Here I can turn off the grid if I want to. And this is it. This is the layout. Oh, I didn't get my connections. There was an error there. I didn't get my routing. I think I didn't specify the routing in encounter, maybe. Maybe I didn't export my routing in encounter. That could be a possibility. Yeah, that's probably the reason why. But normally you'd have the connections here, the wiring, the metal, and everything. And what you can do is that you can go into an individual gate and see it. Or you can extract the whole netlist and spice and simulate it. You can do LVS with your schematic. You can do a bunch of things here. Measure power. But this will take a lot of time, so people usually don't do it. Okay, let me see here again what I did. Say DF top 2 open. Oh, I'm loading. I should save it. Save DF top 2. I think I did save the route here. Maybe I should do save trial route. So let me try the import again one last time. Just bear with me. Import DF lab 3 synthesis 2 and stop 2. Tech lab. Where? Do not create any. It's not selected though. So analog live. Yes, div tech 5. Let's see. Also have 42 warnings. It's still missing. Don't know what the error is, but I can check later. Maybe it's the routing grid. In any case, so this is how you do it. There's something I'm missing, but I still don't know what. Okay. Now I want to show you how you can do the synthesis in Design Vision, but with more control than just running a script. So Design Vision is just a graphical version of design compiler, but it does basically the same thing. Okay, looks like software from '98, but that's fine.
Windows.
Yeah, Windows 95. So, to open my Verilog files, I do File, Analyze, and I add, go to Source, add my files, select, and my format is Verilog, then I do OK. Okay, now here it tells me that it's compiling. This is initial compilation, it's not synthesized. After analyzing, I elaborate. Elaborate, it will, I'll just tell it what the top design is. Just keep this as default, and select your top design. Do OK. Here it will tell me my what do I have in my circuit. Okay, and it will give me the hierarchy. I have a top design including multiplier, divider, and a bunch of things. Okay, now what I should do is that I should specify my clock. So I go into design, attributes, specify clock. My clock name is CLK, and I should select the port here, port, go to clock, select it, it appears here. So the period, let's keep it at 100, so that, 10 nanoseconds. Here the default unit is nanoseconds, so it rises at 5 and it falls at 10. And this is how it would look like my clock. Okay. After I specify my clock, I'm going to specify my input delay and my output delay. To specify my input delay, I go into select, pins, ports, input ports, and I deselect the clock so that I have all my input ports selected, and my input delay from the falling edge is, or the rising edge, let's give it rising edge, 0.1 and 0.1. What does this do? I forgot. Add delay. Anyway, I think this should be selected. And then we select the output ports. You can see this is more complicated than the script, but it's you have more control. Oh, there's a bug here. This doesn't start. I don't know why. The operating conditions, keep it typical and keep this library selected, and then the load on my outputs. I mean, what are my outputs driving? So I keep the output selected. My capacitive load should be, you probably do it as 10 inverters, so type port. This is more easily done in the script because you can specify it to be 10 times the inverter. Oh, the drive strength. You use your inverter as your driving cell. So inverter. Okay. So I couldn't specify my output delay. The load, it's 10 times the inverter. So let's just say 0.1 femto. It's already in femto, so let's just say 10. Okay. And it crashed. Okay, so this software is buggy. But you can see this running the script is much easier. By the way, what you can do is that you can modify the script so that it doesn't quit here. And I advise you to do that. And then start design vision. And here, tell it to execute script. Choose that script. Okay. So it will compile and do everything without exiting. So you could still do more operations afterward. By the way, you can specify a minimum area for your design. So Synopsys will try to compact your design to fit that area. Okay, so here I can actually view my schematic, although it's not really helpful at all to view the schematic. You'd have to be a genius to figure out what's it connecting together. So there's that, but viewing the reports here is actually very easy. You just go to design, report design for instance, and you could see here actually report design will not tell you much stuff. Report area will tell you the area. My total cell area is, for instance it will tell you your combinational area, your non-combinational, and the whole area is, this is in micrometers, so it's 6,500 micrometer square. So it's not too big, it's acceptable. Report timing, report area. One thing I would like to show you finally before we all leave home is the slack. I talked about the slack here, and then it's a critical path. You could actually visualize it here. You don't change anything, and here it will tell you the worst and the best slack. So here all my paths will meet the slack, and they all have for instance my worst slack is 5.84. remember, it has to be positive. The less my slack, the worst. So this is my best slack. If I had bad slacks, they would be in red here, they would be negative. But here I have 10 paths. See here, 10 paths that have 5.84 slack. I have 10 paths that have 6.04 nanosecond slack. This is very useful when you don't know which of your signals is actually creating the errors. slowing down your circuit. Check timing, this will do the same thing. Report path timing. This is the timing report, just to show you the slack here, the worst slack. Okay, and oh, by the way, you can visualize the slack on the schematic, meaning view the critical path on the schematic. Let me see if I can do that here. Yeah, I think those blue lines are my critical path. In any case, I think this is enough. As I think you should be able to do synthesis on your own now and take it into Encounter. Encounter is the same thing. You can skip the script stage and do everything by yourself. The steps are: get the netlist, then place and route the cells. I'm sorry, just place the cells. It will place your AND, your adders, everything. After that, Encounter will do routing, and this is a very complicated stage. Okay, so that's it, and I'll send you your homework